Today, I want to give a short introduction on Adaboost. First, let's note that it stands for adaptive boosting. And talking about boosting, you might think of bagging at the same time. What is the difference between boosting and bagging? Bagging is short for bootstrap aggregation. Bootstrap aggregating it involves training multiple learners in parallel on different random samples of the training dataset. Their results are then combined using majority voting for classification or averaging for regression. Boosting, on the other hand, trains learners sequentially. At each step, we train a new weak learner focus more on the errors made by the previous ones, gradually improving the model's overall performance. We can think of it as building a learning model that evolves over time. So what does the learning model looks at any intermediate step, say step M? At step M, we will have already trained totally M weak learner, and we combine them in a linear combination way. When I talk about the weak learner, here they are usually a stump. A decision stump is the simplest kind of decision tree. It has only one split, so two children. It gonna predict either yes or no directly for the given data set. So how to find the alpha for step n to assign it to the newly added decision stump HM? Well, this question is related to the other question, or I should say it's equivalent to the other question. Well, how could we improve the performance of this evolving learning model over time? Firstly, we need to find a way to measure how well it performs at step M. To do that, we introduce a loss function which quantifies the model's error or how far it predicts R from the true values. If we sub in the loss function, we can see clearly how the loss will change from step M to step M plus 1. I hope my handwriting makes sense. It's just like a mathematical induction. Um, Here we're using a simple math trick. E to the power of a plus b equals a to the e to the power of a times e to the power of b. After the massage, we can see we make a constant here. At front of the whole expression involve hm plus 1 and alpha m plus 1, right? Because at this step, the cm is already a known. It's a known variable. It's a known function. With this understanding in mind, let's just do another trick, renaming. Now I just rewrite the whole expression on the clean blackboard. We know that there are totally n data points. If I just rename it, like for the data point 1, I rename this whole expression as w1 and w2, w3 up to wn. Well, there shouldn't be any problems, right? W1 up to Wn, they are just constant. At this step, they are all known constant. Looking at the other component, we know that when we use the new stump decision tree to make decision, there are totally two possibilities. Either we correctly classify the data point, or we misclassify the data point. So the total loss at step n plus 1 could be written in this form. Basically, we could divide it into two parts. One part is where the decision stump correctly classify the data points. We sum up all the We sum up all of those expression of all those data points. The other part is where the stump made mistake. We also sum up the corresponding given weight and the corresponding loss. Here, since we're using a decision stump, we know that the result is either 1 or minus 1. 1 for yes, minus 1 for no. Yeah, so here we could simplify the expression. So the hm plus 1 xi times yi either equals 1 or minus 1, right? Where the model correctly classify the data points, the value of e to the power of minus alpha will be a small number, right? On opposite, if the model make mistake at this data point, the value of e to the power of alpha here will be larger, will be much larger than e to the power of minus alpha, because we know alpha will be a positive number, will be some number larger than 0. So to find the optimal alpha n plus 1 here, we take the derivative towards alpha n plus 1, where is the loss, and we will get to this expression. Note that I still use the same color code. Green means the sum of those whole bunch of expression where the decision stump h n plus 1 make the right prediction, and red means where the sum of those where h n plus 1 make the wrong decision. Let the derivative equals 0, solving this equation, and we got the final answer.